developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, I'm Professor Thomas Juliano in the Aerospace and Mechanical Engineering Department at the University of Notre Dame. I'm speaking with you today from the AFOSR-Notre Dame Large Mach 6 Quiet Tunnel here at the Whitefield Laboratory on Notre Dame's campus. My AFRL Hub project is to investigate the impact of shockwave boundary layer interactions on surface heating, and in particular, what if the surface was thin like a flight vehicle and that surface heating caused the panel to bulge and thus impact the fluid flow that's causing that heating. A shock wave is formed where the surface has this corner. That shock wave leads to a high pressure increase and very high heating downstream of it. That high heating would potentially distort the surface of a flight vehicle, which would in turn affect the location of the shock wave and the heating distribution. This coupled problem is known as a fluid thermal structural interaction, and it's a complex challenge impeding our progress to successful hypersonic vehicles. Our experiments, conducted here in this wind tunnel, use infrared thermography to measure the surface temperature distribution and background-oriented Schlieren to measure the off-wall density fields. The first step was identifying the baseline configuration that we wanted to study. We selected this cone flare geometry because there's a wealth of information that we've already studied in this lab and others, for instance at the Air Force Research Laboratory, to understand what happens for an undeformed shape. Then we worked with a company called ATA Engineering to predict what a flight realistic vehicle would change into when its surface panel started to heat up. The engineering machine shop at the University of Notre Dame then fabricated a replacement part for the model with that deformed surface. We installed that replacement part and repeated our experiments to see how the off-wall density field and the surface temperature distribution varied thanks to the changed surface. What we found so far is that the peak heating on the deformed panel is appreciably higher than the heating distribution on the undeformed panel. Furthermore, what had been a straight line of flow reattachment and peak heating is now curved due to that bulging surface. We can quantify the displacement of the peak heating and also the magnitude of the peak heating, feed that into future calculations to understand what the next stage of distortion of the surface would be. The information that we've collected so far has been forwarded on to our collaborators at the U.S. Air Force Research Laboratory, Mike Spotswood and Zach Riley. They are experts in fluid thermal structural interactions and are excited to be able to use the detailed measurements that we have made to improve their models of this phenomenon. We're also collaborating with Professor Leanne Dewan at Ohio State University, an expert in computational fluid dynamics. He's going to be simulating the fluid flow in an attempt to more deeply understand the influence of the deformed surface on the flow and how that in turn affects the heating. Future work on this project will involve computational analysis by Professor Leanne Dewan at Ohio State University. And then we hope to extend the project further by looking at flexible panels that will react dynamically as they are heating up, so we can see over the course of one of our wind tunnel runs how the flow field would evolve.
So understanding how structural deformation can affect the local loading is crucial to both the design and life prediction of high-speed vehicles. Now, our experiments aim to study an aspect of this problem by focusing on how local deformations can affect the peak heating associated with shock boundary layer interaction. An exciting next step of this work is to model our experiments using high-fidelity fluid simulation. This will shed insight into the effects of facility noise levels and allow us to extend our findings to quieter, more flight representative environments.